Modern nuclear energy is a triumph of industrial engineering. Operating these facilities requires artificial fuel and heavy containment structures designed to withstand extreme thermal pressures. Inside, technicians rely on thousands of sensors and precision control rods to maintain the delicate balance of the fission reaction. Without this constant monitoring, a reactor would quickly fail. So, when researchers in 1972 began analyzing routine uranium ore from a mine in Gabon, Africa, the results were highly unexpected. Every natural uranium sample on Earth contains exactly 0.720% of the fissile isotope uranium-235. But the samples from Gabon were depleted, showing a concentration of only 0.717%. Nuclear physics provides only one explanation for this specific isotopic drop: that 0.003% of the uranium-235 was missing because it had already been consumed in a fission chain reaction. The evidence points to a single conclusion. A self-sustaining nuclear reaction occurred deep underground in Gabon roughly 2 billion years ago, long before the first artificial reactor was ever conceived. To understand how this occurred without human intervention, we have to look at how 4 specific components aligned in the Earth's crust: fuel, a moderator, a control mechanism, and containment. First is the fuel. Modern reactors require high-speed centrifuges to artificially enrich natural uranium to a concentration of about 3% uranium-235 to sustain a reaction. This raw uranium ore from the Oklo site clearly didn't have access to mechanical enrichment technology. The solution lay in the physics of radioactive decay. Uranium-235 decays much faster than the heavier uranium-238. If we move the timeline back 2 billion years to the Proterozoic eon, the ratio of uranium-235 in the crust increases. 2 billion years ago, natural uranium was pre-enriched by time itself, providing the exact isotope ratio needed for a nuclear chain reaction to begin. However, high-quality fuel is dangerous on its own. Without a way to moderate and control the neutrons, the uranium would simply overheat and the reaction would stop. In the Francovillian Basin, groundwater provided the second component. Water seeping through the rock layers collected directly within the uranium-rich formations. This water acted as a moderator. When a uranium atom splits, it releases fast-moving neutrons that would normally zip right past other atoms. By colliding with water molecules, these neutrons slowed down enough to strike and split neighboring uranium atoms. The water also provided the control mechanism. As the reaction intensified, the resulting heat caused the water to boil into steam. Because steam is less dense than liquid water, it could no longer slow the neutrons, and the reaction halted. Only after the rocks cooled and the steam condensed back into liquid water would the reaction resume. This thermodynamic cycle created a natural pulse, safely regulating the Oklo reactors for hundreds of thousands of years without ever reaching a meltdown. The final requirement is containment. For modern energy systems, storing highly radioactive byproducts for thousands of years is a major challenge. Fission creates toxic byproducts like neodymium, ruthenium, and even plutonium, elements that must be kept out of the biosphere. At Oklo, these byproducts were generated in an open geological environment, yet they never leaked into the surrounding ecosystem. Natural aluminate and clay minerals surrounding the reactor zones trapped the radioactive elements. Over the last 2 billion years, the most dangerous waste products moved only a few centimeters from their point of origin. These Gabon deposits serve as a 2 billion-year field test, providing evidence that under the right geological conditions, radioactive materials can remain stable and isolated over extremely long timescales.